EE300 Linear Circuit Analysis 2, Module 2 Video 8 Network Function Design. In this video, we'll look at where we've gotten to so far, and then we'll look at how to do some network designs to implement network functions. So we'll do first order voltage divider design, and then we'll use a voltage divider with a non-inverting amplifier, and then we'll do inverting amplifier design, and then we'll see how you can do overdamped second order circuits this way, and then we'll have a summary and the previews of what's coming next. So where are we with this stuff? We started with the Laplace transform. We looked at Laplace transforms, the inverse Laplace transform, how to solve differential equations using Laplace, and how to transform circuits into S-domain components where the resistors went to resistors, capacitors went to impedances 1 over CS, and inductors went to impedances LS. And then we saw we could think about things in terms of network functions when we were talking about the zero state responses. We had driving point impedances and admittances. That's the ratio of the voltage and current at a particular pair, a terminal pair. We could have transfer functions between a branch variable at one terminal pair with another branch variable, a different terminal pair. We saw about the response to exponential inputs, that when you put an exponential input into a linear circuit, that the driven component of the output was the network function evaluated at the frequency of the input times a given input. We talked about the properties of poles and zeros, the poles being the natural frequencies and how they determine the modes of the circuit, the natural responses, and how the zeros determine what inputs don't come out. We also talked particularly about the step response and the impulse response and how you can measure the step response to get the properties of the network. But up to now, we've been doing circuit analysis. It's always been given a circuit, find the differential equation, or transform the circuit to the S-domain and find the response. Or here's a circuit, find the network function, or sometimes using an analytic properties going from graphs, like given a step response, how do you determine pole locations and how do you figure out what the network function is? We want to move into design. Design's more fun. Given a network function, it's going to be a multi-stage process. We're going to start by designing what we call a prototype circuit that will be using component values that aren't realistic, but that let us get to start on this thing. Then we're going to scale the component values up to realistic values, and then we can build and test. If we were in a lab situation, we would build the circuit we design and compare the implementation with the expected behavior we'd get from the analysis of the network function we're looking at. And we're going to do this by example, sort of tutorial basis. Instead of you could go through every possible first order circuit and or first order network function and figure out a set of rules given the relative sizes of the pole location and zero location. Well, what would you do? But it's really more fun just to do these things by hand, by letting them tell you what you need to do when you get the network function. So we're going to do these by examples. So let's start with just basic first order voltage divider design. We've been doing a lot of voltage divider analysis. Let's work this the other way around. Let's start and do some design. So here's a network function we'd like to implement, 1000 over S plus 1000. Let's implement that using resistors and capacitors. And this is the general process here. You factor an S out of both the numerator and the denominator. So you get 1000 over S over 1 plus 1000 over S. And you say, well, that's a voltage divider. The Z2 would be 1000 over S and Z1 would be 1 ohm. So you say, oh, that's a voltage divider between a 1 ohm resistor and a 1 millifarad capacitor. And so you draw that and say, this is called the prototype design, the prototype circuit. These aren't what you call realistic component values. You don't really find 1 millifarad capacitors. If Radio Shack was still in business, they wouldn't be there. You may find 1 microfarad capacitors, and so we'll talk about that here in a second. So there's a general property here that we can change the component values by scaling them with a multiplicative factor. And if we increase the size of the resistor and decrease the size of the capacitor, we're going to get the same network function. That RC that we remember from the time constant of circuits, it's going to stay the same if we scale K up and scale C down. So what do we mean by realizable values, though? Well, there's actually a set of standard values, and you're probably sort of aware of them from having been in lab already. 1, 1.1, 2.2, 3.3, 4.7, 6.3, 6.7, 7.2, 8.2, etc. And capacitors have similar distribution. They're sort of logarithmically scaled is what it actually is. So we like to get the resistors, and you don't really find resistors, bigger than 10 mega ohms, your sort of standard resistor size, and you don't find them smaller than 1 ohm. And there's reasons to go with bigger values, but you don't want to go too big because there's noise considerations that are beyond the purview of this class. Similarly, capacitors, you don't really find 1 millifarad capacitor. You don't really find that many. This sort of, between 10 picofarads and 50 microfarads is your basic size here. So they got to be somewhere in there. You don't find them outside those ranges. You can make them, of course. You can put them in parallel. You can put 100 of them in parallel or something if you needed to get something bigger, or put 100 of them in series if you need to get something smaller. But that's a pain. You don't want to do that. So in this case, we pick just a scale factor of 10,000. We get a 10 k ohm resistor and a 100 nanofarad capacitor, or a 0.1 picofarad capacitor, however you want to think about that. And this is perfectly realizable this way. So these are actually shell. You could go to the lab and go into the parts bins and find components near these values, if not exactly at these values. Let's do this again. Here's a different network function, similar. It's instead of having 1,000 in the numerator, it's got 750. So we go the same way. We factor out the S, so we get 750 over S over 1 plus 1,000 over S. And then again, we see the voltage divider, except it's not quite as straightforward this time. You have to sort the 1,000 over S into 250 over S and 750 over S. And now you can see the 1 plus 250 over S would be the impedance in the series branch, and the 750S would be the impedance in the output branch. So when we go to design the prototype, we have a 1 ohm resistor with a 1 over 250 farad capacitor in series with a 1 over 750 farad capacitor. And here, this time I picked 4/3 million as a scale factor. And when you do that, you get a 1.33 mega ohm resistor, 3 nanofarad capacitor in the series branch, and a 1 nanofarad capacitor in the output branch. This is pretty straightforward. It's doable. It's methodical. There's a little bit of insight required, but it's not something where you just churn mathematically to try and get the right answer. It's a straightforward design process, and it's fun. So here's another one. Here's S over S plus 500. So this time we'll factor out the S, and when you do that, you get 1 in the numerator, and you get 1 plus 500 over S in the denominator. So you see the voltage divider now between a 1 ohm resistor in the output branch and a 1 over 500 farad capacitor in the input branch. Again, scaling here, picking K 1,000, that turns the resistor into a 1 k ohm resistor, and the capacitor turns into a 20 microfarad capacitor. Well, all good things must come to an end, and that's the simplicity there is coming to an end now. So there's a little complication here. What if we have 2,000 over S plus 1,000? Well, we'd go the same way, proceeding usually. It worked one time. Let's try it again. So we factor out the S. We get 2,000 over S over 1 plus 1,000 over S, and then we try and identify the voltage divider. And to get the 1,000 over S into the denominator, you have to have the 2,000 over S in the output branch. You have to have a minus 1,000, 1 over 1,000 farad capacitor in there someplace, a negative capacitance. Well, there is no such beast. So we're going to try something different, which is to take a scale factor out of the denominator. So we're going to write the denominator as 2 times 1,000. And now we have 1,000 over S plus 1,000. We know how to implement that. That's going to be a 1 ohm resistor with a 1 over 1,000 farad capacitor, just like we just saw a minute ago. But now we have this scale factor of 2. And so we recognize that as a gain term, and we implement that with a non-inverting amplifier. So here we do the voltage divider and the gain circuits, and then we put them all together. So on the left, you see the 1 ohm resistor in series with the with the output branch being the 1 over 1,000 farad capacitor. And then we have this little op amp with a gain of 2. You just have a 1 ohm resistor in the between the inverting terminal and the output, and a 1 ohm resistor between the inverting terminal and the signal ground. So we can do a scale factor for each module there, each component circuit individually. So the voltage divider here has a scale factor of 1,000. So the 1 ohm goes to a 1 k ohm, and the 1 over the 1 millifarad goes to 1 microfarad. But we use some big resistors over here in the non-inverting amp, because basically, think about it. You've got this voltage drop V2 going across these two resistors, and you're splitting that so you get V2 over 2 at the minus terminal. There's no reason to have a lot of current flowing down that path. None's going to go into the minus terminal. So if you put big resistors there, it basically just sets up the voltage divider with very little current flow, little power. And so it just saves, you're not wasting power of your circuit. Say you're running this thing off of batteries. You don't want to waste a lot of power just having current flow so you can set up a voltage divider. You could also put the op amp on the input side. I didn't put that in the slides here, but I think you can imagine how you would just put the input into the plus terminal first, have the gain factor, and then have that feed the 1 k ohm and the 1 microfarad capacitor divider. Well, let's look at something different, inverting amplifier design. So here's a different network function, and here's something new. It's got a plus minus there. It says plus minus S plus 2000 over S plus 1000. What does a plus minus mean? It means we don't care whether when we put the input waveform up, if the output waveform goes up or if it goes down. We're happy to have an inverted output relative to the input. It doesn't matter. We're just interested in the signal shapes and what happens in the temporal properties of the waveforms, but we're not really interested in whether putting a plus waveform gets me out of plus waveform. I can always invert it later if I have to. So we're going to use an inverting op-amp circuit to do this. And I know it's tempting, and because we use impedances so much, we like to think of the inverting op-amp as minus ZF, the feedback branch, over the ZN, or ZS, the source branch. But in this case, it's really, if you use admittances instead of impedances, it makes it easier to implement these circuits. So we're going to think of the network function implemented by the inverting op-amp as the negative of the source branch admittance over the feedback branch admittance. And we're going to do that because admittances in parallel add. And that makes things simple because the admittance of the capacitor SC and the admittance of the resistor then is 1 over R. And so S plus 2000 in the denominator there, in the numerator, would be the source branch admittance, and that'd be a 1 farad capacitor in parallel with a 1 over 2000 ohm resistor. Of course, you're not going to go out and buy a 1 over 2000 ohm resistor or a 1 farad capacitor. You're going to scale these into the standard values. So here's our prototype circuit. The 1 farad, you can see the S plus 2000 there on the left on the source branch, and the S plus 1000 on the feedback branch. And so to scale these, this time I picked 10 million as a scale factor, and you end up with a 100 nanofarad capacitor in parallel with a 5 k ohm resistor on the source branch, and a 100 nanofarad capacitor in parallel with a 10 k ohm resistor in the feedback branch. So that makes that kind of thinking makes it really easy to implement those first order S plus something over S plus something kind of network functions. We can get into more details at another time about why this is a preferable design to having a series capacitor with a resistor to implement the design, as you'll get if you do it using the minus ZF over ZS form for the gain of the inverting op-amp. Whereas there's reasons you'd rather have that capacitor in parallel with the resistor rather than having it in series resistor. All right, well, we can do this to think about an overdamped second order network. You know that you have first order poles for a second order network that's overdamped. They're all on the negative real axis. So let's look at the network function 3 million over S squared plus 3000 S plus 2 million. We're going to factor the denominator, and then we're going to distribute the numerator across the various parts of the denominator. So I think you can see the S plus 1000 times S plus 2000 there. That gives us, if we were to use the design we've done earlier, 1000 over S over 1 plus 1000 over S for one of the networks, and 2000 over S over 1 plus 2000 S for the other network. But the product of 1000 and 2000 there is only 2 million, so we need an extra scale factor of 1.5 there to get the numerator up to the specified 3 times 10 to the 6. But we can represent this now as two first order circuits with a 1.5 gain non-inverting amplifier connecting them. So on the left is the 1000 over S plus 1000 circuit, 1 ohm resistor with a output branch of 1 over 1 millifarad. And then here's our op amp with a gain of 1.5. And then here's the 2000 over S plus 2000 on the right, which is a 1 ohm resistor, and then the output branch is a half a millifarad capacitor. So we can scale these, and again, you can use a different scale factor for each of the 3 different networks here. So the left network, I use a scale factor of 1000. The middle network, again, to keep the current flow on that op amp low, so that I'm not draining current, just running down there, setting up that voltage divider. I get 50k ohms over 100k ohms. And then I picked 10,000 for the other one, so I get a 10k ohm resistor and a 50 nanofarad capacitor. So that's pretty much it. That's how you do first order and cascade of first order network design. So you can do this in R's and C's, voltage dividers with op amps to do a non-inverting amplifier, or you can do it using inverting amplifiers if you don't care about the inversion. If you care about the inversion and you want to use it on inverting amplifier circuits, you can always do a gain of -1 to get it fixed back. We could do overdamped second order networks, and we could actually overdamp cascades of arbitrary order overdamped circuits, because as long as we have a set of poles on the real axis, negative real axis, we can implement each one of those poles with a first order circuit, and then we just need to correct the gain, and we need the non-inverting amp in there to avoid loading, so that the one circuit doesn't drain current from the other circuit. It wants to drain the current from the op amp using the power supplies of the op amp, but doesn't want to drain current from the input network, because that would screw up the input network's behavior. We can extend this to second order networks. I think you can imagine that, and you will probably explore that on the homework. So where you have R's and L's and C's, and so you can have underdamped networks. And then we're also already exploring on the homework how you can get underdamped second order behavior with networks of R's and C's and op amps. And we'll come back to that for extended discussion later in the term, because that's the core circuit that's going to let us do filter design. So what's coming up, we're going to move into the third module of the class, which is frequency response. We'll start that by talking about the sinusoidal steady state. Then we'll look at the frequency response of first and second order circuits in particular, just to see sort of how they behave prototypically. And then we'll do Bode's famous method and look at Bode plots as ways of characterizing frequency response. And then we'll also be able to look at Bode plots and figure out where poles and zeros are, and go back and do the design based on measured frequency responses. So this has been Module 2, Video 8, Network Function Design. This is EE300 Linear Circuit Analysis 2.